Hello and welcome back to Differential Equations, section 2.7, Electrical Circuits. So in this section we are going to see another application for our non-homogeneous equations with constant coefficients. And before we actually do this, just a little, should I say, review or overview of components that will play the role. So I'm just going to draw a circuit and we'll discuss every aspect of it first. So, electrical circuit. In order for current to flow through a circuit, you have to have a circuit closed, which means the switch that you see here has to be closed. You also have the source, which could be battery or electrical generator. So you have a source, and once you close the switch, the electrical current, which is motion of electrons through the wire, will start flowing through the circuit. We have three basic components here. There is a capacitor C, which stores and releases charge in coulombs. Then we also have an inductor L, which is another energy storing device which works through magnetic fields, and we have the inductance in it, which is called L in Henrys. And then we also have a resistor, which is purely a spender. So you can think of a resistor as a light bulb or hair dryer, or electrical stove or heater. So resistor will actually heat up and convert some of the electricity into heat. So with all of these components, once you close the switch, the current is going to start flowing through the system, and we actually have. Since we have these three different, three different things, each one of them will, I hate using the phrase use some of the, of energy voltage provided. So how does it work? Think about the pipe through which the water can go. If the pipe is flat, the water is just going to stay in that pipe. But if the pipe is tilted, it will flow from the higher potential, right? It's potential energy from higher potential to the lower one. So the same thing happens with the electrical circuits. If you have a battery is producing this difference in potential between positive and negative, and then the current flows through the branch. Now, what we do is we can think about it. It's not exactly what's happening, but we can think about it that way, that each one of these components is going to use up some of that potential for it to work, to operate. It's not exactly what's happening, but it's maybe the easiest way to understand what is happening. We call these voltage drops, and the sum of all voltage drops have to add up to the source, because the source is producing a certain amount of energy, and all of that energy is used in the circuit because there's nothing else hooked up to it. So when we are looking at the circuit, let's say that the voltage provided is, 10 volts, then two components are 4 volts and one component uses 2 volts, so altogether 10 volts, and we're all good to go. So we are talking about this idea of the voltage drop. And that idea of the voltage drop is given for inductor L as L di dt. For a resistor, R is just R times I, no calculus involved. And for capacitor C is 1 over C times charge Q. So this is what we have. And as I said before, what you do is you add up all of these voltage charges. So L di over dt plus ri plus 1 over c q to get your voltage source of energy for the system. So this is what we have in terms of that. Now what I'm going to do is I'm going to define that the current in terms of I is the change of charge over time. So if we just have a charge sitting somewhere, it doesn't do anything. Now, if the charge starts changing, which is the derivative in respect to time, you are experiencing flow of current. So what I'm going to do now is I'm going to plug this into the equation above and see what I get. So I'm just going to plug this in. And I will have L times d dt of dq dt plus R times dq, come on, erase, dq dt, I don't need the parenthesis, plus 1 over cq equals e to the e of t. Now the derivative of the derivative is the second derivative, so we can easily write this as LQ double prime plus R times Q prime plus 1 over CQ equals to E over T. Now, guys, L is a number, R is a number, 1 over C is a number, so this definitely is a first order linear non-homogeneous differential equations with constant coefficients. And you probably know a lot of people that can't even spell that. You know what each word means. So, second order, right? Second order, nonlinear, non-homogeneous differential equation with constant coefficients. There's no way I'm going to write all of that out. And now we're just going to recast this into a current, because most of the time what we are worrying about is what is the current. The reason is you can have wires just as thick. The more current requirements, the thicker the wire. That's, you know, why you shouldn't be swapping your 15 amp wires with fuses with 20 amp fuses, because your wires in the wall are still 15 rated. The more current, the more heat, so on. So these things have to all grow proportionally in order for us to have this equation. So now what I'm going to do is I'm going to take and recast this. So I'm going to take one more derivative of this, but that actually changes everything into currents, because we see that dq dt, which is this term here, right, that would change into a current. So if I am to take a derivative in respect to time, I would have L now second derivative of dq dt. You see how that's still three derivatives, right? I just decided to write them like this. So take the second derivative of this first derivative. Plus R times the derivative of dq dt plus 1 over c dq dt, and on the other side you just have e prime of t. So each time where you see this, you know that's I, because we have it over here. So what I'm going to do now is I'm just going to write this as L I double prime plus R I prime plus 1 over C I equals to E prime of T. Here's your boss equation. So we want to do this for currents rather than charge. No one chases charge around, right? Now, what type of electricity we're talking here? We're talking alternating currents, not the direct ones. Direct currents have a flat source, which is direct source. So you see, that's just your battery. This kind of source here is going to be sine or cosine wave, which is alternating currents. So thanks to Nikola Tesla, right, we have today, electrical systems as we have. He was the one who invented the alternating currents, transformers, generators, electrical motors. Well, he technically did everything that we use today. So it is. This is for alternating currents because this E, the forcing term, is going to be given in terms of sines and cosines, which are the waves for alternating currents. So so alternating current source E of T is going to be E0 sine omega T. Now you guys heard about the 50 hertz and 60 hertz and all of those things, right? At 110 volts. So here's the piece that deals with volts, right? And here is the one that deals with frequency. What is the meaning of 50 hertz or 60 hertz? It means that it swaps its polarity that many times a second. So when you have a battery, which is direct current, you have a plus and minus sign of the battery, and the plus sign is always a plus sign for that battery. When you have the alternating currents, and let's say you take a look at the two prongs in the wall, once something is connected to it and the current starts flowing, current is changing its direction 50 times or 60 times a second, depending where you, US or elsewhere in the world. So in US it's 60 hertz. 60 hertz means that it changes its direction from plus to minus 60 times per second, because hertz is 1 per second. And that's in this omega, captured in the omega. You know that the sine wave, right, how it looks like, and then this omega gives you that, scales it into a second. So the rest is a joke. The rest is the same as previous problems. So this was the theoretical part to see where mathematics leads into everything else. Now we just do our undetermined coefficients. I'm going to tell you that the L is 3 and R is 7, and and you just do the same thing like we did for equations that will have 1, 2, 3, 4 currents, and you have to solve systems to figure out how much the current is in each of the branches. Now with Kirchhoff laws and these couple differential equations, that's actually going to be another lecture. And you guys, okay, great. Yeah, okay, fine. Awesome. So let's take a look at a situation here. It's problem number 4. It doesn't really matter which one we do. They're all the same. So what do I have? I have in the circuit the figure 277 with the switch in the position 1. Suppose that. So I'm just going to draw without the switch because we don't really need the switch. So we have the generator there. We have the resistor here. We have the inductor. That's L, and it goes back into the source. So Come here. No, come here. Come on, come quickly. Come, you're holding up the class. Come on. Is there a capacitor in the picture?
Oh, this is a new one?
Yeah.
Oh, I thought
Okay, cool.
I thought we were still working on the last one.
I said problem number 4.
All right, never mind.
Oh, thank you for the question. So we have that L is equal to 4, L is equal to 2, R is equal to 40. So 2 Henrys, 40 ohms, and the E of t, alternating current, we have 100 volts, e to the negative 10t. And we also have initial condition I0 equals 0, which will help us get the particular solution later. Find the maximum current of circuit for, cool. So what are we going to do now? Well, all we do is we plug everything in. We don't have a capacitor, which means the last term is going to be 0. So I have L, which is 2, I double prime plus 40 I prime is equal to the derivative. Now that's one of the biggest mistakes, guys. The equation, look, you see this? Let me, there we go. And then I circle it. All right, you see there? Can't miss it, right? So you have to plug in the derivative of this here. So that's going to be negative 1000 e to the negative 10t. Bueno? So now we have our equation. This is our model. And now we need to solve this. For those of you more perceptive, right, you would immediately see that you have double prime and a prime. You can do a reduction of order. But, you know, let's put that under the carpet. Like, why simple if we can complicate things? So let's do it. So what do I have? Again, current is going to be, is going to be the complementary part plus the particular part. Complementary part is from the homogeneous case, the left-hand side, and the other one is from the right-hand side, which is the variation. So let's go. We have 2r squared plus 40r equals to 0. Factor out 2r. This r looks like an exponent. It's not just exponent. 2r, and we are left with r plus 20 equals to 0. So r is equal to 0, or r is equal to negative 20. Right? So what I get here is the solution that I, complementary, is equal to C1. I'll write Z0t plus C2e to the negative 20t, and then I'm just going to, it's not 0, it's 1, so C1. So IC is equal to C1 plus C2e to the negative 20t. So that's the complementary part. Cool.
So how do you do reduction of order?
Or just you make substitution. Say U equals I prime,
Okay.
and then U prime is I double prime, and just plug them in. So, yeah, and you integrate. When you get the answer, you just integrate once. So this is what we have, right? And you would see that you would get this plus C from the integral, right, when you go back. So, but anyway, but I digress. I hate that when someone says, try to be more important than they actually are. A particular solution. So what do I get for particular solution? It is negative 1000 e, so function is equal to negative 1000 e to the negative 10t. Is it? Yep. And now we find a whole bunch of derivatives, but guys, you know what's going to happen, right? This is e to the t function. It's going to keep changing the coefficient in front, but it's always going to be this. So I get that the solution here, the IP, is equal to some kind of a e to the negative 10t. That's all I have. And I know its derivatives. Negative 10a e to the negative 10t. And second derivative, positive 100a e to the negative 10t. And now we plug this in our equation, which was 2 double prime 40 prime. So 2 times 100, so 200a e to the negative 10t, plus 40, so minus 400 e to the negative 10t, needs to be equal to negative 1000. What was the original one? 1000 e to the negative 10t. From where we see this is negative 200, so, I forgot a over here. So a is 5, right? You have negative 200a e to the negative 10t is equal to negative 1000 e to the negative 10t. Divide both sides, right, by this, and a is equal to 5. So what is the answer? The current, like the total current, is the complementary solution, which we have as C1 plus C2 e to the negative 20t plus 5 e to the negative 10t. Remember that you always pick up the one that was your pattern, and then you do that. So now we also have that I of 0 is 0. So we can plug that one in. And when we plug that I of 0 is 0, I get 0 is equal to C1 plus C2 plus 5, right? Is that true? C1 plus C2, because when you put this to be a 0, right, it becomes 1. Yep, okay, good. So I have that equation C1 plus C2 is equal to 5. Wait, I'm supposed to have one more for C2. The circuit of the figure with the switch position 1, suppose else. There is something else that I need to know here, which I apparently don't know. Let me see if I can fish out that second condition anywhere. What would be the second condition? I mean, I could just write it in terms of one constant, but I'm not happy with that. That I of t is equal to, and now write C2 in terms of C1. So it will be C1 plus, and C2 is 5 minus C1 e to the negative 20t. So I eliminated one of the constants, but I'm not sure what the other condition is. It's not given in the text. It's not given in any of these. They only give one. There is something somewhere that yeah, maybe it should be derivative, first derivative equal to 0, but why? That's my question. The first derivative of the current. Why would derivative of current be 0? That's my question. Yeah, I'll have to meditate on this to find out. But this is how the problems are done. Again, same stuff, same methods. It's just you carefully place where L and R and C are, and you just compute. So nothing special, nothing new, other than this theoretical part that we're missing here, which is we don't know where the what the other condition is. So guys, we are done with chapter 2. Let me just stop the stream. Bye.